All right, so this is going to be our kind of last stoichiometry focused video for the moment. And this is going to involve something called enthalpy, which has to do with thermodynamics. And we're going to talk a little bit about it here, but I'm not going to get into too much about it. We'll revisit enthalpy when we talk about thermodynamics again later. So enthalpy, of course, you know, it's abbreviated as H because why not? It is a measurement of the energy in a chemical system. However, it cannot be directly measured, so therefore we talk about it as a change in energy in a chemical system, which means we are going to talk about it as delta H, because hopefully you're familiar with delta from mathematics. If you're not, delta means change. All right, so delta H, the change in enthalpy. Right, and this is a measurement of the energy or heat, right, that is moving in or out of the system. And here is the little mathematical equation, right? Delta H is equal to the sum of the heats of formation, right? So this is heat of formation in the products, right? So notice that products comes first, minus the sum of the heats of formation of the reactants, right? It is final minus initial. That's pretty much what you're going to get every time you have delta. You're going to have something that is a final state minus an initial state. This is no different, right? So the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. And heats of formation, right, these you would look up in a chart, in a table, in a book, someplace. You are not expected to know these. So that's how you calculate delta H. Right, this can also tell us about whether a system is gaining or losing energy, right, based on the sign. So these two terms, endothermic versus exothermic. Endothermic, a process where energy is absorbed by the system or moving into, right? So there is a positive value for delta H because it indicates that energy is moving into the system. And then the other one, exothermic, right? This is a process where energy is being given off by the system. So a negative value for delta H indicates that energy is leaving the system, right? So we always express these in terms of what's going on with the system. So if energy is moving into the system, delta H is positive. If it's exothermic, energy is being given off or moving out of the system, it's a negative value. Okay, enthalpy in chemical reactions. So first, we're going to need a balanced chemical reaction, which I just happen to have here. You may recognize this as a combustion equation from when we talked about balancing combustion equations. And the question that we might ask is, what is the enthalpy of reaction for the combustion of hexane, right? Hexane right here, 6 carbons, hexane. And to answer that, we are going to do some calculations. First, we're going to calculate delta H for this equation. And so we look up values for the heats of formation of our products, water and carbon dioxide, right? And so we find them on a chart. So here, carbon dioxide has a heat of formation of negative 393.71, and I'm pretty sure that's kilojoules per mole is the unit for that. And we multiply it by 12 because there's 12 CO2s in this reaction. And then we look up water, and in this case, right, we look up water vapor, which will be very specific because water vapor and liquid water have a different heat of formation. And so this negative 241.84 kilojoules per mole, because there's 14 moles in this balanced equation, we multiply that by 14. So then from that, we subtract the heats of formation of the reactants. So we look up the heat of formation for hexane, and that would be negative 167.2 kilojoules per mole. And we multiply that by 2 because there's 2 moles of hexane in the balanced equation. And then here, you'll notice 0 for oxygen, because in an elemental state, things do not have a heat of formation. That is considered their standard state. So there's no heat of formation for elements. Now that we have all our heats of formation here, we've looked them up, we've put them into this equation, we do some math. And we find that we have negative 7,775.88 kilojoules per mole. Now, we're going to need to remember that number because we're going to use it in stoichiometry. So we have our same balanced chemical equation, and now we have a new question. How much energy is released when 24.3 grams of hexane is combusted? Remember when we looked at delta H previously? I'll just go back here, right? It had a negative value, so we know that this is exothermic, so we know energy is being released. So we can ask the question, how much energy is released when we burn 24.3 grams of hexane? And we're going to treat this just like any other stoichiometry, right? We have this here, but then we ask, where's our B? What is our B? Our B is energy, right? And we calculated a value that we're going to use in this stoichiometry when we calculated delta H. But we're going to start off just like any other stoichiometry. Oh, there it is. I even put it up there. I was thinking ahead. So we start off 24.3 grams of A. We can put that over 1 times the molecular mass of hexane, right? Because that's our A. Make sure our grams are canceling out. Then we have our mole ratio. So here, right, we know our moles of A, 2, it's in our balanced equation. And then moles of B, we consider this to be 1 mole of B, right? So we're just going to put 1 mole in there. Then we use our delta H, our enthalpy that we found in the last equation, right? All our units are canceling out except for kilojoules, which is great because kilojoules is a unit of energy. And we do some math, and we find that when that much hexane is combusted, that reaction releases 1096.3 kilojoules of energy. Just what you always wanted to know, and now you know it because you've used some enthalpy and stoichiometry to find out how much energy is released when hexane is combusted. So there we go. That is enthalpy and stoichiometry. We will talk more about enthalpy when we talk about thermodynamics, but for now, that is it.